All right, today we are looking at another one of the easier sorting algorithms, which is insertion sort. As usual, I'm going to start off looking at the very general idea of insertion sort, and then we'll look at how you go about programming it for a list and an array. As with the previous videos, I'm not going to show any actual code, but if you are familiar with how to manipulate lists or arrays, such as moving elements around in them, removing elements, stuff like that, then it should be pretty easy to write the code yourself from that point. So let's get started with the general idea of insertion sort. As usual, we're going to be trying to sort this set of items from smallest on the left to biggest on the right. So the general idea of insertion sort is we have this list of items existing, and we are going to pull an item out and start a new list. Similar to selection sort, but in insertion sort, it sort of doesn't matter which item you grab. We aren't looking through to find the smallest item like selection sort. So there's a couple different ways insertion sort is done, but usually you just grab the one on the left and we're going to move it to its own list. And the reason what we're doing here is we are creating a list here that this list is going to be sorted, but this is not necessarily going to be the final location for this object. So we're going to insert more elements into this list, and we're going to adjust this list as necessary to keep this list sorted. So we're going to grab ourselves another element here, and we're going to insert it into this list, which currently only has one thing. So for that to happen, this one is smaller than this one, so it needs to go before that one. So we're going to move this one to the right so that we can put this one in here. And now we have our sorted list, and we grab ourselves the next thing that we want to insert into our sorted list. So in this case, this new one is smaller than both of them, so it needs to go to the left of both of those. So let's move these so that there's enough room to put it there. And again, we have kept this new list sorted because we keep inserting items into the correct sorted position for this list. So next one is just going to go at the end here. List, because it's bigger than everything that was in the list, so still sorted. The next one is going to need to go in the middle here to keep this all sorted. So we're going to move these so that there's room to put this in here. And of course, still sorted. So yeah, the last couple, we're gonna just figure out where this needs to go and put it in its proper location. Figure out where this needs to go and put it in its proper location. And that is how you sort with insertion sort for the very general idea of it. So now let's look at how we're doing it with a list. So with a list, insertion sort is extremely similar. We are going to start off with, immediately, we're just going to grab the first node and start a new list with it. And then we're going to keep track of, we're going to be comparing the next node that we want to insert into the list with the nodes in the list. We're doing a doubly linked list here. You can do it with a singly linked list also. So with a doubly linked list, you can go from the back to the front or the front to the back, trying to figure out where this new node should be inserted. With the singly linked list, you have to go from the front to the back. So I'm just going to go from the front to the back, and we're going to traverse our sorted list down here, which currently only has one thing. And from front to back, and we're going to insert our new node before the first node that is bigger than it. In this case, the first node here is bigger than it, so we are going to move this over. We're going to move this over so that we can move this down here. So that that's in its correct place now. And then the next iteration, we're going to bring this back up to the first node of the original list up here, or the updated original list here. And then we're going to start back at the front here, and we're going to say, okay, we're going to traverse with here, and we're going to say, okay, let's find the first node that is bigger than the new node that we're inserting. In that case, it is here. So visually, we're just going to move all this stuff down so that this all fits. But in reality, keep in mind, we're only changing the pointers of these linked list nodes, which would be these little arrows here. We're not, in reality, actually moving the nodes. We're only changing the pointers. All right, so now we've placed that new node on the list, and we go to our next iteration, which is we start over with this and that, and we keep doing this. So we're going to traverse our sorted list, looking for the first node that is larger than the node that we're trying to insert. So none of these are larger than the node we're trying to insert. So this is going to end up at the end of our new sorted list. And we just keep on doing this. So start over here. We say, okay, is one less than, or sorry, is 1 greater than 3? No. Is 2 greater than 3? No. Is 5 greater than 3? Yes. We're going to insert the 3 before the 5. And so visually, for this to make sense, we are going to, oops. We're going to move this over so that we can squeeze this 3 in here. And then continue on with the next iteration. So we're going to find the first node that is bigger than a 6. So we're going to traverse, 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 and say, okay, Let's move this over so that we can put a 6 in here. And then next iteration. And then we traverse, traverse, traverse. So that we can fit the 4 in here. Whoops. That didn't quite work. And now that the list that we were pulling from is empty, we are done. We have sorted our linked list with insertion sort. Now let's look at the array approach. The array approach is a little bit less intuitive compared to the general and list approach. It's the same idea, but trying to do this in place in an array is just a little bit less intuitive. So we're gonna walk through this carefully here. So initially, since we're doing this all in place, our first element is already where we want it. We're not going to move it yet. So this here is the sorted part of our array. The rest is unsorted, and we're going to grab items one at a time and insert them into the sorted part, and the sorted part's going to grow and the unsorted part is going to shrink. So that's what we have these pointers for. So we're going to start looking at the second item, and essentially we're going to pull this out because to insert an item into an array, we need to shift all the items that are bigger than it to the right. So we're going to pull this one out, and we're going to say, okay, is the item to the left of our green arrow here, is that bigger than the item that we're trying to insert? And we're going to say, okay, yes, 5 is bigger than 2. So we're going to shift it over. And then we're going to go over here. And then there's nothing to the left over here to compare anymore. So we're just going to put the 2 in here. And then we are going to go to the next iteration. So at this point, the 2 and the 5 are sorted. So next iteration is we're going to pull out the 1 here. And we're going to say, is 5 greater than 1? Yes. Let's shift it to the right. Is 2 greater than 1? Yes. We're going to shift it to the right. And then again, we've reached the end of the array. So that's where our new item is going to go. And then we move to the next iteration. And of course, this section of the array is sorted. But again, this is not like selection sort or bubble sort where we are locking elements into place where we never have to compare them again. We still have to compare elements to these if they are bigger or smaller. So a little bit different in how it works from those other sorting algorithms. The other thing is I'll talk about that a little later, actually. Let's continue. So, next iteration, 7. We're going to pull that out here, and we're going to say, is 5 greater than 7? No. So we're going to just put the 7 right back where we had it. We're not doing anything with that. And we can move on to the next iteration. so now this whole section of the array is sorted. All right, now we're going to talk about what I wanted to mention here is a little bit important for speed of how quick the insertion sort algorithm is. And it's very important that you are not swapping it's very important that you are not swapping elements to the left like that, because those swaps are a lot slower. That's a big reason why bubble sort is very slow, is because it does a lot of swaps. And swaps are essentially 3 moves, whereas the way we're doing this here is we're pulling this out, that's 1 move, we're comparing, and then if it's bigger, that's 1 move to move that over, and then we're comparing, that's 1 move to move it over. We're comparing, and the 3 is, sorry, the 2 is not bigger than the 3, so we're not moving the 2 over, we're just putting the 3 in its place, so that's 1 move. So we did, essentially it's like 1 swap and a couple other moves instead of multiple swaps, where each swap is 3 moves. So that is very important that you do it that way if you want your algorithm to be fast. I've seen animations of insertion sort which seem to imply that you are doing swaps, but that's not how the algorithm actually works, because that's basically a slower version of the algorithm. All right, so we just put the 3 in there. We are going on to the next iteration, and now all of these are sorted. So we're going to pull out the 6. 7 is greater than 6. We're going to move it over. 5 is not greater than 6, so we're going to put the 6 in its place. Going to go on to the next iteration. And of course, all of these are sorted. So we're going to pull out the 4 here. 7 is greater than 4. We're going to shift it over. 6 is greater than 4. We're going to shift it over. 5 is greater than 4. We're going to shift it over. And 3 is not greater than 4. So we are going to put the 4 in its place. And now we're done. So that's the array version of insertion sort. Slightly trickier than sort of the general idea and the list idea, because you got the sorted and unsorted part of the array all in the same array. But hopefully that explanation made it clear. So now some last notes about insertion sort. First of all, we're going to talk about the space complexity of insertion sort, which is big O of 1. That is, you need a few extra variables, but it's a constant amount of space that you need to implement insertion sort. So yeah, you got yourself a few temporary variables for the algorithm, but nothing. You're not storing an additional copy of the array or part of the array or anything like that. So, as with bubble sort and selection sort, very good for space. For for time complexity for insertion sort is big O of n squared. Exactly how fast insertion sort is depends a lot on the initial set of data. So if we look at the array version of insertion sort, each time you're inserting a new element, the amount of time that's going to take depends on how far to the left it has to go, because that's going to determine how many shifts that you have to do and how many comparisons you have to do. So if the array is already sorted or nearly sorted in ascending order, like we were trying to do, then you'll have very few operations, and then insertion sort is very, very fast in that situation. It basically becomes big O of n if the array is already sorted. But in the average random case, it's going to be big O of n squared. You're going to have to move the new node or the new element about halfway in, on average, about halfway into the array. Whereas if the initial data is sorted in descending order and you're trying to sort it into ascending order, then each time you are trying to insert into that array, you're having to shift everything to the right. In which case, then insertion sort becomes much slower than the average case. So in the average case, it's, I believe, somewhere around twice as fast as selection sort. In the slowest case, I think it's about the same speed as selection sort. And then the best case, it is much, much faster than selection sort. You could also, well, let's just leave it at that. It will depend, of course, a little bit on if you're using the stable or unstable version of selection sort. But I don't have exact numbers of comparing these two algorithms with actual data, so that's just a general idea of how fast they are relative to each other. Selection sort, you have to go through the entire unsorted array each time, whereas in insertion sort, you're on average going through about half the sorted array. All right, so last thing is is insertion sort stable? And yes, insertion sort is stable. You just have to make sure you write your conditions carefully. It's going to depend on you just gotta you gotta be careful with how you code it. So if you're doing it in an array, you need to stop when you get to the element that is equal to it. And then you're doing it with a linked list. Like it's going to depend on if you're going from the front or the back end of the linked list, and but just be careful with your how you're coding it. You'll probably want to make yourself a quick example to make sure you're doing it Make sure you're doing it right. And that's all there is to insertion sort. So that's the last of the kind of the easier sorting algorithms, which are all big O of n squared for time complexity. So they're all considered generally slow, but insertion sort is on average definitely the fastest of them. So yeah, it's pretty good, but yeah, faster than bubble sort for sure. Should generally be faster than selection sort. And then the other sorting algorithms we haven't got to yet, we're going to be looking at merge sort and quick sort and counting sort. I'm still trying to decide the order of those. Merge sort and quick sort are very easy to explain the general concepts of, but the array implementation of them is a bit of a pain. I'm gonna have to draw a whole bunch of stuff on the screen, and it's gonna be a pain. So I might go to counting sort next, but counting sort's got its own challenges, so we'll see. But those are all good algorithms to learn.